Now we are going to see about band theory of solids. Okay, it is one of the very important topic, right? So in this band theory of solids, what we can know, yes, it is used to know about the electron behavior of a particular molecule. We can predict the electron behavior of a particular molecule. Okay, and also the band theory of solid is an extension of molecular orbital theory. You have heard about this word, that is bonding, anti-bonding and all in molecular orbital theory, right? So it is the band theory of solid is the extension of molecular orbital theory. And what we can exactly predict from this band theory of solid means we can know whether a material is a conductor or semiconductor or insulator. Okay, we can know from this band theory of solid. We have to know two important terms in this band theory of solid. One is valence band, another one is conduction band. Okay, so always the valence band in energy diagram, always the valence band which is present in lower energy level. Okay, it is always present in lower energy level and it is always filled with valence electrons, right? It is always filled with valence electrons. The conduction band is present on the higher energy level, that is above the valence band. Okay, so the conduction band present on the higher energy level, it is always empty. Okay, yes. Now, by using energy diagram, we are going to find out which one is conductor, which one is semiconductor and which one is insulator. Okay, okay. This is energy diagram. Here, this is nothing but of valence band and this is called conduction band. Okay, so here in this the valence band is present in the lower energy level and conduction band is present in the higher energy level. Okay, so here there is no energy gap between the valence band and conduction band. Here there is no energy gap. So what actually happened? The electron, valence electron which are filled in the valence band can easily move to the conduction band and it can conduct electricity easily. Right? So it acts as this material is considered as the conductor. The example of conductor is copper, silver, etc. Right? So next one is semiconductor. In semiconductor, there is a little bit gap between valence band and conduction band. Okay, the gap is 1 electron volt. Okay, so here it is not possible that valence electron can move up from the valence band to the conduction band. So in this case, we have to give some external energy, whether it may be temperature like that. Okay, so if you are giving external energy, the valence electron which are present in the valence band can easily move to the conduction band and it can conduct electricity. Right? So this material can be considered as semiconductor. An example for this is germanium. Okay. So next we are going to see the insulator. So here it is clearly seen that there is a large amount of energy gap between the valence band and conduction band, that is 5 electron volt to 10 electron volt. Okay, so here the valence electron which are present in the valence band cannot move to the conduction band to conduct electricity. Okay, so it acts as the insulator. It acts as the insulator. The example for insulator is wood and glass. Right? Okay. Generally, the metals may be the conductors. The metalloids may be the semiconductor, right? And non-metals may be the insulators. Now, in CSIR net questions, they will be asking, they will be giving you some ranges, 3 to 4 ranges like this, okay. They will be asking from the ranges which one is conductor, which one is semiconductor and all, okay. So, in that time you have to know it, right. So, conductor means it has the range of 10 power 4 to 10 power 7. it has the positive charge. Okay, so 10 power 4 to 10 power 7 ohm inverse minute inverse. Okay, in conductors, when we are giving heat to that material, what happens actually? Conductance gets decreases because there will be no energy gap between the valence band and conduction band in conductors. Okay, so we don't want to give the heat and all in conductors. Okay, if you are giving heat, then only the conduction gets decreases there. Okay, the flow of electrons will be getting slow in the conductors. So what actually it says, the temperature is inversely proportional to conductivity. If we are giving temperature, the conductivity gets decreases here, right? So in the case of semiconductor, it has the range of 10 power minus 6 to 10 power 4. Okay, ohm inverse, minute inverse, right? So temperature is directly proportional to conductivity. It is because we have already seen that there is little bit energy gap between the valence band and conduction band. So the valence electron which are present in the valence band cannot easily move to the conduction band to conduct electricity. So we have to give the external source for that, right? So if you are giving temperature, the conductivity gets increases. So temperature is directly proportional to conductivity in the case of semiconductor, right? Then the conductors and semiconductors and the insulators values of conductivity and resistivity I have given here. Okay, here from this table we can clearly say that the conductors like silver and copper having the highest positive value of conductivity, right, and it has the lowest negative value of resistivity. Okay, so and in germanium acts as the semiconductor, right? It has the middle value like 1.5, 0.6. So in the case of insulator, rubber, wood and all, it has the very high minus charge of conductivity and very highest positive charge of resistivity. So from this table what it concluded? So conductivity is inversely proportional to resistivity. Okay, so as the conduction charges increases, resistivity is decreases. Okay, conductivity decreases, resistivity increases, right? So from the table we concluded that, right? So then types of semiconductor. Okay, so types of semiconductor has been classified into two types. One is intrinsic semiconductor, another one is extrinsic semiconductor. Okay, so what is intrinsic semiconductor? Intrinsic semiconductor is nothing but of pure semiconductor. It will be in pure form. There will be no impurities in this semiconductor. Okay, so without any impurities, nothing but of intrinsic semiconductor, right? So here if you are giving temperature to that material semiconductor, number of electron which are present in the valence band will go to the conduction band. Okay, the electron present on the conduction band gets increases if you are giving this, if you are giving the temperature. Okay, so the electron population which are present on the conduction band can be explained by an expression. Okay, that is nothing but of sigma is equal to sigma naught e power minus Eg divided by kT. Here Eg is nothing but of width of the band gap. This equation will be look like Arrhenius equation in chemical kinetics, right? So next one is extrinsic semiconductor. Extrinsic semiconductor means that is pure form of a material which is treated with small impurities. Okay, so we will get the semiconductor that is nothing but of extrinsic semiconductor. Okay, so here in pure form we are adding small impurities. No, so this process is said to be the doping. This process is said to be doping, and this type of extrinsic semiconductor can be classified into two types. One is P type, another one is N type. So what is P type? In P type semiconductor there will be the positive holes present. Okay. In the N type semiconductor there will be the excess electron which are present in the conduction band. Okay. Now this is the N type semiconductor and that one is P type semiconductor. Okay. So here silicon has 4 valence electron. Each silicon has 4 valence electron to make the bond. Okay. So here arsenic has the valence electron of 5. Okay. So these two bonds involved to make one bond. It will make one bond. The extra one electron of arsenic, okay, is present in the system. Okay, this is nothing but of extra electron. Okay, so this is called N-type semiconductor. N-type semiconductor means which are present extra electron. Okay, so here in the system there is one extra electron is present. So in the case of P-type semiconductor, silicon has the valence electron of 4 and boron has the valence electron of 3, right? So it will make a bond. Okay, so here it will make a bond. Here one electron is here. Here this is a hole. Okay, here there is no electron for it because boron has the valence electron of 3, right? So it has hole. Boron has hole. Actually, the electron from the silicon will move here to fill this gap. Okay, so in that time here electron will be coming. So it will make a bond. What happens here? Here the hole will be produced. Okay, so it will go on like this, right? So this is nothing but of P-type semiconductor, positive hole semiconductor. Okay. So next one is example. Example for this N-type semiconductor is Fe2O3 Mn O2. Usually N-type semiconductor all are having higher oxidation state like +4, +3 like that and all. In P-type semiconductor, it has the example of FeO, MnO like that, and it has the lower oxidation state, right? Now the application of semiconductors. Okay, so semiconductor acts as the diode, right? So what actually it does? It actually converts alternating current into the direct current. It converts the alternating current into direct current, right? So and also it acts as the LED sources. LED is nothing but of light emitting diode, right? Next one is barcode scanners. If you go to any supermarket, there will be the barcode scanners, no? So that are not made up of by semiconductors only. Then it acts as the photovoltaic cell. It is nothing but of solar cell. Okay, what actually it does? It converts sunlight into electricity, right? It also acts as the transistor. It is used to amplify the electrical signals. Okay, thank you.